We're very happy to have them to visit us and give us the top cotangent bundle as a Coulomb branch.
Yeah. Okay. Well, thanks. Thanks for the invitation. So, if you're a mathematician, you might find yourself giving a talk at the string math seminar and ask yourself, well, how did I get here? So, you know, back a long time ago, I was a student here, right over there. And I got interested in symplectic resolutions of singularities. And then someone told me, that this was in New Jersey, not here, that all the interesting examples of these actually came from 3D n=4 supersymmetric quantum field theories. And they gave me this paper to read, which was probably written in this building, that explained that all of the interesting examples of those came from brane configurations in type 2B string theories. And then I ended up here. You know, who can explain it? All right. So the story about 2B string theory, I won't try to explain in detail, but Hanani and Witten, this was now about 30 years ago, were thinking about this, of configurations of D5, NS5, and D3 branes in type 2B string theory. And out of this 10-dimensional story, they sort of looked at what happens when you specialize to the plane of the D3s, and you get a 3D n=4 supersymmetric theory, which you can describe as a quiver gauge theory in a linear or a cyclic quiver. And somehow the quiver comes from this x6 direction. And you'll sometimes see these pictures. So I'm going to use red for D5 and blue for NS5. And sorry to the colorblind people in the audience. Someone who is colorblind, you know, told me a little while ago that they can't see the difference between red and black, which just is a disaster for me. So you'll see this picture of, you know, this is in the x6 direction. So D5 and NS5 branes come at particular times in the D6 direction, and then the D3 branes sort of lie along the x6 direction and join them. And you can read off what your quiver gauge theory is by how the D3s connect up with the D5s and the NS5s. So in particular, if all the D3 branes end on NS5 branes, then we can describe our theory as a quiver gauge theory. In this situation, we call this co-balance. This is Nakajima's terminology for it. The nodes correspond to gaps between NS5 branes. So here I have 3 NS5 branes. There's one node that corresponds to this gap, one node that corresponds to this gap. So I get my 2 nodes. The rank of the gauge group, which is a UN, is the number of D3 branes joining the 2 NS5 branes. And I get a bifundamental between every consecutive pair of those, and a fundamental for every D5 sitting between the NS5s. So this is sort of the kind of big picture physics reason to be studying these quiver gauge theories, but they're also very interesting for me. We'll get to that in a moment. There's also a dual picture where you're balanced, where everything ends on a D5. And it's exactly the same story. And you might say, well, wait, doesn't the difference between D5s and NS5s matter? And the answer is yes, but where it shows up is that the supersymmetry acts differently.
I've never seen these diagrams before. Is there something relevant to the fact that some of the black lines continue through the red line, some of them end on the red line?
What's relevant here is between the red lines, how many black lines are there? So that's telling us the VI in Nakajima's terminology. And you know, if they ended somewhere else, I would get some theory that doesn't necessarily have an obvious quiver description. So if you look in Nakajima's bow varieties paper, he just uses. It doesn't matter that there are, whether they kind of match up or there are gaps. What matters is the number of them. So like if these guys didn't match up, that would be okay. That would be the same. Yeah, okay. Great. Okay, so how is the supersymmetry different? I'm trying to pack too many things into this talk. You can see how many circles I have. So let me not get into too many details, but because I have a 3D theory and I have n equals 4 supersymmetry, there are two topological twists. This has to do with the fact that spin 4 is SU2 times SU2. The two twists correspond to the two factors of SU2. And applying these topological twists, I get two local operator rings in the two different twisted theories. When I do the A twist, I get the chiral ring for the Coulomb branch. When I do the B twist, I get the chiral ring for the Higgs branch. So somehow, if all of that was nonsense, and I'm sorry, maybe I shouldn't have brought it up at all, the point is, out of one of these sort of combinatorial configurations, you get two rings. They're commutative rings, so they're actually functions on some spaces, which are the spaces called the Coulomb and Higgs branches. So these are two spaces that are associated to my quantum field theory. And it turns out they're often natural spaces that you know about. All right, so the reason I had sort of the same looking description for whether I was ending on D5 branes or NS5s is that there's a symmetry in the type 2b string theory, the S duality, that swaps the A and B twists and swaps the D5 and NS5 branes. So this allows us to get what's called three-dimensional mirror symmetry, and sort of the first interesting calculations in three-dimensional mirror symmetry, as far as I know. It probably depends on what you think is interesting. But the ones that I found about first anyways, were sort of found using this approach, where there wasn't any more elementary way of seeing that this had to work out. So in the balanced case, we have a nice description of the Coulomb branch. It's the Nakajima quiver variety corresponding to this quiver gauge theory. So if you're a mathematician who thinks about this stuff, these pictures, there's sort of one thing that mathematicians know how to do with these, which is to construct a group, U3 times U4, construct a representation, which is this one I said about combining bifundamentals and fundamentals, and taking a hyperkähler quotient. So that's the Coulomb branch of a balance theory, or dually the Higgs branch of a cobalance theory. So you're more likely to have heard this called a Higgs branch. But because of this duality, we can think of it as either one. More generally, as long as these brane configurations aren't too bad, we can write the Higgs and Coulomb branches as what are called Bow varieties, which have been introduced by Cherkis. And this was proven by Nakajima. All right, any questions? Okay, so there's a really powerful observation here due to Hanani and Witten, which is that you can start reordering these branes. And there's a simple combinatorial rule for how the configuration changes. When I swap a red and a blue brane, a D5 and an NS5, the number of D3s between them needs to change, and it changes according to the simple algebraic rule. I look at the number of D3s on the outside, I sum those together, I add 1, and the number of D3s I had before and the number of D3s I have after have to sum to this guy. So for example, one of the examples I'm going to be talking about a lot in this talk is T star CPN. So the corresponding affine algebraic variety, right? I was talking about having a commutative ring and taking its spec. So I should be getting an affine variety, is the rank 1 matrices that are n by n. And those have a sort of maybe more familiar geometric description. I can take the cotangent bundle of CP n-1. So that's a choice of a line and a linear map whose image is in that line and which kills the line. So that's something that's rank no more than 1 and whose square is 0. That's the Springer resolution of this guy. So I can think about this one way as the Higgs branch of this quiver gauge theory, right? This is a Nakajima quiver variety corresponding to, so I have U1, and I'm looking at n hypers. So I would think of this as C2n, or maybe, ooh, no, more canonically as T star Cn. And if I take the hyperkähler quotient of that, I'll get T star of Cpn minus 1. If I take generic moment map, and if I take zero moment map, I'll get this singular affine guy. All right, any questions about that? So the corresponding brane configuration is 2 of these NS5 branes, and then n D5 branes in the middle. Hopefully I didn't switch my 2 names. And then 1 D3 brane that goes all the way across. So, right, I have 1 gap between NS5 branes, so 1 node. I have n things in the middle, so I have n copies of the fundamental representation of U1, which get sort of doubled if I'm doing everything n equals 4. And I have that 1 D3 brane going between them. So that's why it's U1. All right, if I want to describe this as a Coulomb branch, then what do? I swap NS5 and D5 branes. I go from being co-balanced to being balanced. And I do Hanani-Witten moves to get back to being co-balanced. So I swap red and blue, and then I say, oh shoot, I want everything to end on blue, not on red. Did I swap something? No, okay. Did you have a question? No, okay. All right, so now I want things to end on blue and not on red. So I need to fix that, and I need to do a Hanani-Witten transition where these guys swap, right? And I take the number on the outside, add those up, and add 1, and that is the sum of the number of old branes in the middle and new branes in the middle. So 1 plus 0 plus 1 equals 1 plus 1. So I'm still going to have 1 brane in the middle after I swap. And now everything ends on blue. And so I look at this picture and I say, okay, what quiver gauge theory does that tell me? Well, now I have many gaps between blues, right? Upstairs I had n red branes, so now I have n blue branes and n minus 1 gaps between them. So I'm going to have n minus 1 circular node. I still only have 1 D3 brane, so I'm going to have 1 everywhere. And then I have 2 reds on the very outside that give me 1 and 1 here. An important subcase, the simplest one to always keep track of, is what if we had had n equals 2, so this is n equals 2. So I do that swap, and I just get the same thing back. So n equals 2 is self-dual. All right. So in both cases, I have 2 and then 1 here, and that goes to itself.
Sorry, I have a question. You're saying when you swap the blue and the red, and then you want to change the...
Yeah, so I swap the Higgs and Coulomb branch, right, when I do that.
Right. So when you do the Hanani-Witten move, you want to pass to each other, pass each other.
Yeah.
You change the number of D3.
Yes.
Why can't you keep doing it like in the other pictures?
Oh, well, because here, that's a fair question, because I will mess up being co-balanced if I do that. Right, so when I swap these two, I have 1 on the outside plus 1 on the outside plus 1 is old plus new, right? And I have 1 old, so if I swap these again, then I get 2 in the middle.
Yes.
So now it's not co-balanced. I'm worried that I have swapped red and blue at some point. But you know, I wanted this situation where all of the D3s end on blue branes. Right? I mean, this rule that I have for getting a quiver gauge theory out, it's no good if I have guys that end on red branes. Yes, exactly. And so I do Hanani-Witten moves until I get that condition, and then I can turn things into a quiver gauge theory. Yeah. So yeah, the important upshot out of this is that if I want to write T star of Cp n minus 1 as a Coulomb branch, I use this quiver gauge theory. And then Hanani-Witten transitions tell me that that's the one to consider.
Sorry. If
Yeah.
something's not cobalanced, is there a unique situation where it becomes balanced or cobalanced?
So there can be situations where you just can't get there. But if you can, then yes, I believe it's unique. And you know, it's one of these things where you can write down some slightly complicated formula for, you know, that'll tell you the right thing. Okay, but I'm supposed to tell you about Grassmannians. And of course, Cpn minus 1 is a Grassmannian, but it's not a very interesting Grassmannian. So if I want Grassmannians, I have to put more black strands in the middle. I have to have more D3 branes. So the quiver gauge theory that gives me T star of a Grassmannian is this one. I'm always going to assume that K is less than n over 2. So my affine variety, the cotangent bundle of the Grassmannian now is, right, I have a subspace that gives me a point in the Grassmannian, and I have a linear map whose image lies in that subspace and whose kernel contains that subspace. So that's going to be the matrices that square to 0, because if I land in that subspace, I'm in the kernel, so if I do it again, I get 0, and where the rank is no more than k. And you see that this will get weird and confusing if you let k be greater than n over 2, because there aren't any maps square 0 with rank more than n over 2. So that's an example where you can't get back to being co-balanced if you put more than n over 2 black lines in the middle. And you'll see when you do this procedure, I'm not going to do this in enormous detail, but if I have this procedure where I have k d3s in the middle, ns5s on the outside, and n d5s in the middle, well, what happens when I do my first switch? Right, the calculation is, well, I have k plus 0 plus 1 is equal to k plus 1. So I end up with 1 D3 brane here. And I'll note here, I haven't done the flipping the colors. I haven't bothered with that. So I'm trying to get a configuration where everything ends on red. And now I do this flip again. And instead of having k plus 0 plus 1, I have k plus 1 plus 1. So I get 2. And then I do the flip again, and I get 3. And I keep on going on towards the inside. And you'll see if I have more than n over 2 black branes in the middle, I'll end up with some extra ones between this blue in the middle that I can't get rid of using Hanani-Witten moves. That's telling me the theory is bad. Or possibly ugly. If I think if n is 2k minus 1, then it's ugly. All right, so this is what I get when I translate that into a quiver gauge theory. What do I have? I have a linear quiver, and I have rank 0, then 2, then 3, etc., up to k minus 1 to k. And there might still be a bunch more reds in the middle. There are n minus 2k reds in the middle. So I have a span here where it's all k's, and I have these two 1s on the outside. So this is the relevant quiver gauge theory whose Coulomb branch is going to be T star of the Grassmannian. And maybe I'll just mention here, this guy has shown up other places before, right? We know what the 3D mirror of T star of the Grassmannian is. It's the Slotavy slice for 2 Jordan block nilpotent. So this is the quiver gauge theory whose quiver variety is the Slotavy slice for a 2 block nilpotent. All right, any questions? Probably. Oh my God. Where does the time go? What a disaster. All right. I won't go into this in detail, but you can also get T star of flags the same way, and that's actually self-dual. And kind of the nice way to see that is you have this description where it's easy to swap red and blue, where you have blue and red with 1, blue and red with 2, blue and red with 3, etc., all the way up. Okay, so why was I telling you about this? I better speed up. So we're supposed to be, or I'm interested in, I think some of you are interested in, coherent sheaves on symplectic resolutions. And there's this sort of very fascinating perspective on these. Let me just skip to the end, where you can relate, for example, coherent sheaves on T star of the flag variety to representations of U of GLN, but in characteristic P. And in particular, Bezrikov and Mirkovich tell me that if my P is big, the derived category of coherent sheaves on T star of flags that are supported set theoretically on the flag variety is equivalent to the derived category of representations of this Lie algebra. And this is kind of a crazy fact. It's conjectured this is true for all P, except I think a few very small ones, but sort of the proof is for very big P. And I say this in characteristic P because, of course, I can study this category in characteristic 0. But if I went to characteristic 0, this category would be totally messed up. So if I want a characteristic 0 version of this, I have to have some replacement for... Sorry? Yeah. Oh, yeah, I guess this conjecture. Yeah, this conjecture only makes sense in characteristic P. But you would hope for there to be some replacement for this guy. And I claim that there is, and it's not too bad, but if you want to find it, you have to think about T star of flags or similar kinds of varieties, for example, T star of the Grassmannian, as Coulomb branches, not as Higgs branches. So mathematicians are used to thinking about these, for example, as symplectic reductions, but I argue for this kind of representation theory stuff, it's actually better to think about them as Coulomb branches. Yeah?
Maybe switch back to slides and what's
What's proven is that this is true for some large P.
when I said the DPU is what is the representation?
I mean, this is the derived category. Oh. Yeah, okay, that's weird. It's modules over this guy, finite dimensional modules. I don't know why that didn't match up, but it's just this guy. Sorry? Yes, but I mean, the point is, again, like somehow you have to replace this guy, replace the universal enveloping algebra by something else. I wouldn't call it a category O thing. So what I was getting to, sorry, the question of Can you remove 0? And the answer is yes, if you change what goes on the right-hand side. Sorry?
What is supposed to go on the right-hand side?
Well, something combinatorial. So these pictures I usually draw of diagrams on the cylinder.
I should ask you the question. The first question is, are you talking about something with 0?
I mean, they construct a tilting bundle, right? And so you can remove 0 by saying the thing I should put on the right-hand side is the endomorphisms of the tilting bundle.
But they only compute that at the 0?
Right. I mean, somehow like that tilting bundle, yes, it's left implicit what that actual algebra is. And sort of the point I was hoping to get to here, and which I've left myself not nearly enough time for, is, well, somehow this is...
I don't think you know how long this seminar is.
Oh, okay.
We have just,
Okay, good.
we didn't advertise it, but yeah, our record was just broken, so it's 5 hours.
Okay, well, I have dinner plans at 6, so. All right, good. Well, then I won't rush too much. But the thing that should go here, that works in all characteristics except maybe p very small, is this cyclic KLR algebra, cylindrical KLR algebra. I know I was struggling with that. So that's sort of a replacement for this quantum group that allows you to get rid of the 0 and allows you to work in characteristic 0. And then you can prove that in characteristic P, that also describes the representations of the universal enveloping algebra. All right. Are there any other questions about this piece? Yeah.
If you replace the co0 x as a co of x0 is a compact part.
Uh-huh.
What's the two-phase relation?
So you're asking what would be the replacement here?
Maybe.
I should think carefully about whether all the scheme structures are right. I mean, that should just correspond to modules here that factor through some two-sided ideal. I think that's right, but I would want to think, you know.
Are you making a derived statement or underived statement?
I mean, again, I would want to think carefully about whether it actually works derivedly, but like, yeah. Well, yeah, I mean, somehow it has to be something about getting lucky in that case, but maybe you're lucky. Yeah.
Yeah. Does this equivalence respect the natural tensor product?
Does this equivalence respect tensor products? I guess what I would say is no. No, the subject of tensor products is kind of complicated. I would need to think about it, but the short answer is it's not obvious like how tensor product on one side corresponds to tensor product on the other side. Probably there is some connection, but I would need to think carefully about it. It is actually like a very tricky thing, kind of thinking about the tensor structure on call. Any other questions? Okay. So the question then becomes, well, what algebra am I going to put here? And I kind of spoiled my answer, but let me try to explain how thinking about things as a Coulomb branch might help. The reason that thinking about things as a Coulomb branch helps is that we have an independent description of Coulomb branches, which is not at all obviously related to the description of Higgs branches. And so it gives a totally different description of this variety. So Braverman and Finkelberg and Nakajima tell me if I want to get the Coulomb branch chiral ring, I can write that as a Borel-Moore homology. And it's a Borel-Moore homology of very kind of strange space. So I look at Taylor series in my matter representation, modulo Taylor series in my group. So you can think about this as mapping formal disks into N mod G, which is the same thing as G principal bundles on a formal disk with a section of the associated N bundle. Similarly here, and I take the fiber product of those over doing the same thing but with Laurent series. So the usual picture one draws is this raviolo. So the left-hand factor corresponds to, I have a map of a formal disk into N mod G. The second term corresponds to the same thing. And then when I take that fiber product, I say, oh, I can identify these along the outside. So in kind of terms of the physics, right, I have a 3D theory. And for reasons having to do with the twist, things are kind of holomorphic along the plane transverse to a line. And ooh, I should have made that a different color. So things are locally constant in this direction, but I have some puncture here in the middle such that over the origin, the local constancy doesn't identify these guys. And that's why I get this fiber product, that I can look at what's happening on the top of the cylinder, on the bottom of the cylinder, and then things have to be constant along the outside of the cylinder, but not at this point in the middle. And you can make this sort of more precise by saying that you want to interpret the category of lines in the A-twisted TQFT as D modules on this loop space. And so this is the self X of a push-forward D module. The one corresponding to the trivial line. So somehow what's going on here is this is about what kind of singularities do your fields have when they get close to the line, right? And the trivial line says, well, I don't care what kind of singularities you have, except you shouldn't have any. So that's what this is telling you, that you don't have any singularities in your fields. All right. Any questions? I mean, obviously, this is sort of a big story. Apparently, we have 3 hours, so feel free to stop me and ask me to expand on things. You know, I think I prepared way too much, but probably not that way too much, so. Oh yeah, well, it's a very large stack. Yeah. Yeah. So you can think of this as, I have this guy which people usually call the raviolo, which is, you know, this disk. Wait. Yeah, and it's literally. Yeah, that's true. Okay, yeah, so, right, if you want to think about this sort of, you know, using these usual tricks of, you know, switching between quotients and such, right, you can think of this as stuff that's GT, loop group equivariant on, oh no, sorry. Let me give myself more space to write this. So if I have point mod GT crossed over point mod G round brackets T, point mod GT, right? Then I can interpret that as, let's start writing G of O instead of G of K, as G of K mod G of O on both sides, right? Or as thinking about the affine Grassmannian with G of O acting on it, right? And then if I incorporate this stuff from the matter, that gives me kind of a singular infinite dimensional vector bundle on the affine Grassmannian. And you can sort of, there's some nice way of thinking about the Borel-Moore homology of that guy. And that's what BFN are literally doing. So yeah, I mean, somehow I think this description of it is much clearer, but right, what they're doing is if you pick a trivialization of the bundle on one of your disks, then that gives you a point in the affine Grassmannian, and the other one isn't a choice anymore, so you just have to remember the G of O action. And then with the N of T's, the reason it's sort of a singular vector bundle is you're looking at your section on one of the disks, and it has to extend holomorphically across the other one as well. Yeah, sorry, I remembered the better way to say this. So if I trivialize one of the disks, then what do I see when I'm on the other disk? I see a principal bundle that's trivialized away from the origin. So that's a point in the affine Grassmannian. How unique is that description? Oh, well, I could have changed the trivialization on the other side. That's the G of O action on the affine Grassmannian. And then I have this section which I have to actually make sure extends non-trivially. Yeah. Okay, great. And in our case, G and N come from this linear quiver that we discussed. So I always like to think about complex groups instead of compact groups. But if you were a physicist, you would write U of VI. I take the product of that over the nodes, and I have this matter, which again is bifundamentals plus a bunch of copies of the fundamentals. All right. And I apply the construction on the previous page to this guy. If you want to think about this kind of more concretely, what is that section of the principal bundle? It's really a point in the moduli space of quiver representations with coefficients in Taylor series. And this is, moduli space of quiver representations with values in Laurent series. Right? So the usual way to think about the G action on this space is to think about a point in N as a quiver representation and G as changing basis on it. So finding isomorphic quiver representations. So when we extend scalars, it's just doing that, but with coefficients in Taylor series or Laurent series instead. All right, well, I could do a whole talk, and I have in this seminar several years ago, about how you can describe this algebra. The way I like to explain it is, well, there are scalars in the theory, and those give you a copy of sim of T dual, the dual of the torus, and I should say there's a Weil invariance here. And then you have monopole operators that are indexed by dominant co-weights. And I want to think of my dominant co-weights as paths in T mod W, and scalars as like little coupons that I put on these paths. And when you write things this way, the relations of the Coulomb branch ring become kind of local. You can say locally, okay, when I do this to a path, it has this effect on it. So it's not just homotopy, it's sort of homotopy where at certain spots you have to do something non-trivial. In the quiver case, well, what's my torus? It's U1 to the N, or I maybe should have written to the VI here. And the Weil group is the symmetric group. So I'm looking at a bunch of copies of UN, I'm modding out by the symmetric group acting on them. So I have an unordered N tuple in S1. So how do I draw, how do I think about a path in unordered N tuples on S1? Well, I draw a kind of movie where my points are moving around a cylinder. So I think of height as giving me time, and then as time goes, my points move around the cylinder in some way. And there are going to be rules that are sort of local on here that are doing this kind of homotopy on paths. All right. So the way I would describe these is with these KLRW diagrams. I apologize, a bunch of you have seen these before and this is boring, but yeah, of course.
So you're saying you have some description as paths in T mod W, dissemination, and so on.
Yeah.
Plausibly, like if there was no relation, there's like paths. I mean, description of the category of local systems, the modules of it, I think, we describe it like local systems, right? Is there some in your connectively similar to your path algebra and some secret categories, approaching categories on T mod W?
Probably you could. I mean, it does end up looking like.
But you know what it is?
I mean, I haven't. Yeah, I don't know quite the right kind of sheaf words to say, right? I mean, somehow, what you end up with is your torus gets cut up into regions. You have idempotents corresponding to the regions. And so you could sort of think about that region as carrying like the image of the idempotent as a local system. And then there are some seams between the regions where something more interesting happens.
Okay. But in particular, you don't know a statement like the one I'm saying is false.
No. Yeah, I mean, I don't know. Like with, for example, in the abelian case, you have this torus, it gets kind of cut up into polytopes. And the more geometric thing to do is to like turn each of those polytopes into a toric variety. And then you have a nice kind of like Lagrangian skeleton kind of story. Yeah, it's a good question. And I don't quite know. Yes, yes. I'll get there. But yes, I mean, somehow right. Like for the Coulomb branch, it's, kind of based paths at, for example, the identity, you could say. All right, so what I'm going to describe is the kind of recipe you use for quiver gauge theories to get this description out, where things are a little more concrete. So first, I'll describe planar KLRW diagrams. So this is, I have the plane, and I have curves, which are, they're the flipped over graph of a function from 0 to 1 to R. And they satisfy sort of obvious genericity properties. What are the important things to know? There are two different kinds of strands, which correspond to the circle nodes and the box nodes in the picture I was drawing with the quiver. So there are VI black strands with label I and WI red strands with label I, and that corresponds to the rank of the gauge group and the number of fundamentals. And yeah, so things have a color and they're labeled with one of the nodes from my quiver. The red strands are vertical at fixed X values, while the black strands can move around and do different things. Yes, right. So what's happening here is the black strands are where I am in the torus mod the Weil group. The red strands are describing, like I said, there have to be some spots where something interesting happens. So these have to do with, right, what are the weights of the fundamentals, right? They tell you something about the position of these points. So something funny has to happen at specific positions for these points. And then I said that the scalars you should be able to think of as coupons. The scalars I'll represent with these dots. So that corresponds to a copy of the symmetric polynomials of the corresponding rank by putting dots on these different points. Okay. And everything has to be generic. I never have 3 strands going through the same point. I never have a dot sitting on a crossing, et cetera, et cetera. All right. Now for my purposes, like I said, we're working in the torus, so it's actually going to be cylindrical. It's a collection of curves, which are now the flipped over graphs of maps from 0, 1 into the circle, R mod Z, which I can also think of as U1. So they satisfy the same local rules. No difference there. Any questions? All right. Oh my gosh, something terrible happened here, and it's going to be really hard to remove. Oh, geez. Okay, I probably won't even try. Somehow I accidentally pasted something twice, and it's going to be very messy. Oh my God. Ooh, okay. You're going to have to just forgive me that some of this got a little messed up. I don't know what happened there, but apparently I somehow pasted twice. Ooh. Okay. Okay, so unless I sort of make things non-generic, I can just do isotopy. This was what I was saying about you can just do homotopy of the path. If you homotop the path, what are you doing? You're sort of smoothly deforming your diagram. But then there are certain points where kind of things are bad, and there's an interesting relation for going through those points. I don't know, should we talk about this more? Or you're satisfied there are relations? These will be very familiar to many of you.
That's a question.
Yeah.
How do you determine the sign? Or does it include a single combination?
Okay, so I mean, there are different conventions. I mean, I would say like the sign right, you really are doing some calculation with BFN. So BFN tell you what the algebra is. That's kind of canonical. You then have some choice about like which homology class, right? So every one of these pictures actually corresponds to a homology class. And so these relations all just, come from doing calculations in algebraic topology. But I mean, I have to make some decision about which homology class depends on different things. There are different conventions which might lead you to have different signs.
So, within these relations, it's supposed to be local
Mm-hmm.
on this model.
Right, so whenever you see an equal sign here, that means like if you see a little area, yeah.
Can you explain how these relations work?
I mean, again, it's local in the sense of I have some big complicated diagram, right? I see a little circle that has this picture in it.
I understand it's local in this plane, but it's not locally local to not
I mean, all of these, oh, I see. Oh, okay, good point, good point. Let me think about this. I mean, this is local in the sense that in T mod W, this has to do with looking at the subtorus defined by a root and the subtorus defined by a weight, and looking at what happens when you go around the codimension 2 thing defined by those in 2 different ways.
My complaint is that, that minus this side, that's local.
Mm-hmm.
But on the other side, you have a copy of identity, which is very far away from either of those groups.
Well, I mean, these strands can be as close together as you want them. But I think you might not be thinking about the mod W part, right? That these guys swap, but this only shows up when I and K are equal. So in T mod W, the bottom and the top are the same. So yeah, I mean, if I and K are not the same, there isn't something in W that swaps them, and I'm kind of forced to get 0 by exactly this argument you were saying. But yeah. So this, if you're thinking in the actual torus, this has to do with like, I have 2 hyperplanes, and if I hit them in one order, then there's some relation for if I want to hit them in the other order. Yeah, I mean, maybe I should say, like, you know, somehow I have some hyperplane arrangement that comes from the roots of the Lie algebra and the weights of the representation. And all of these relations come from like codimension 2 things in that hyperplane arrangement. So in general, there's sort of a geometric description of what happens.
You explained this basically a bunch of you before about
Yeah.
how they derive these like the
Yes.
kind of pictures from the relationship.
Yeah. Okay, and as Mina was saying, if I want the actual Coulomb branch chiral ring, I need to just take a piece of this algebra in a way that's going to be really important later. And the way I take a piece is I have to pinch all of the strands with the same label together at the top and the bottom. I think this will be clear when we do some examples. I should mention here, like this pinch, this is really just kind of a notational thing. I think it looks kind of scary because it looks like you're really adding more stuff to the algebra, but it actually just represents a particular element of the algebra. You can make everything. Yes, it's related to that guy. It's a little more complicated. But.
So instead of discussing algebra, you discuss categories where objects are write the question running graph out in a circle.
Mm-hmm. Yeah.
I'm saying taking anamorphisms of one object.
Yes. Yes, exactly. And the reason I sort of need something a little extra is this thing that Peng was mentioning, that it's really, I have an object where all of my strands of different colors are grouped close together, but that guy's actually the sum of a bunch of copies of the same thing, and I have to project down to one of those. So I need to add in a little bit of extra idempotent. Oh. What I was saying is, so you gave this description of a category. And there's an object in the category where, so I have my circle. And I have a bunch of 1s here, and a bunch of 2s here, and a bunch of 3s. Okay. But this object, its endomorphisms are a matrix algebra in the Coulomb branch. So I have to pick out a rank 1 idempotent in that matrix algebra. And this pinching is a way of doing that conveniently.
Oh, I see. But you're saying, like when you pinch them, you don't know which one is which.
Exactly. Yeah.
Do we know how to realize the center of the QRW in diagrams? Like, you're supposed to tell us the center, which is the coordinate.
I mean, the center, of this guy. Well, I mean, wait, the center of which algebra? The whole? I don't know. I would need to think about it. Because I'm not sure what that is.
That's supposed to be the spherical guy.
Well, is it? How does the spherical guy map into endomorphisms of some other idempotent?
No, the point is, whatever the center is,
That's true.
And so and A Coulomb also has to be the thing. If you know in your category the equivalent to modular resolution,
Yeah,
then A Coulomb had better be same.
that's true.
It doesn't mean that this has to be the center. It
Yeah.
doesn't mean it has to have smart.
Yeah. That's an interesting point. Okay. So I promised I would talk about examples, so let's talk about examples. So I want to go back to this T star P11, so let me just remind you what the quiver gauge theory was. So I have a bunch of nodes all with 1, and the two outside guys have a 1 box. So right, the number of black strands with each label is the number in the circular nodes. So I have 1 with label 1, 1 with label 2, 1 with label 3, 1 with label 4, all the way up to label n-1. And then I have red strands with labels corresponding to the boxes. So I have 1 with label 1 and 1 with label n-1. And I don't have to pinch anything together because I don't have 2 strands with the same label. 2 black strands with the same label, I should say. So there's actually a slightly subtle point here, which is I put these guys in this order, but the theorem on the previous page works for any arrangement of them. They can be in any order they want. And I'll always get that the endomorphisms is the functions on the Coulomb range. So I chose this one kind of arbitrarily because it looks nice.
Can you show the theorem on the previous page?
All right. So the theorem on the previous page is if I look at the ring where I put that idempotent at the bottom and that idempotent at the top.
Yeah, I think that, what is that?
Oh, so EC equals any idempotent with all black with same label together. Okay, but then I also have to do this projection to a piece. So when I have n strands with the same label together, right, then I have a consistent set of relations. They're the Nil-Hecke relations. So it's basically these relations, the relations of the Nil-Hecke algebra. And the Nil-Hecke algebra is a matrix algebra. Yeah, exactly. So,
So the thing which is special about this distinguished object, that's the one on which you have no action.
yeah. And so I take any primitive idempotent, which is a sum end of the one where all these guys are together. It means it's a matrix algebra, and I take a rank 1 idempotent. Oh, lots of them. I mean, how many rank 1 idempotent things are there in n by n matrices? Right, I mean, so I have an idempotent where all these guys with the same label are together.
Why do they have to be the same label? Aren't you gonna have to, like, for your T star Grassmannian story, aren't you gonna have to consider guys which are not of the same label?
Okay, so if I want the functions on the Coulomb branch, right, the point is this is the guy that corresponds to the trivial line.
No, sorry, but I don't understand. I mean, in general,
For example, suppose you have only one line in each label. Then his idempotent would be identical.
Well,
if you happen to have more than one strand of a given label, then to describe his idempotent, you have to put the strands together.
oh, okay.
And then when they're together, you have
I see, then, I see, if you have more than one implant, okay.
mean, in terms of line operators,
No, I
okay,
completely understand.
okay.
But doesn't this force you, like, you said that those two guys are equal, where the guy on the left has some higher degree of tangency. So there's some kind of matter of interpretation. Why is the guy crossing as opposed to an uncrossed guy?
Well, I'm telling you that that's the way to interpret it. I mean, what I was going to say is in terms of line operators, right, what I'm getting is like the trivial line coupled to a flag variety. So like here, this is, I have the trivial line coupled to a P1. Pinching means forget the P1. Splitting means remember having the P1. And that's exactly also what corresponds to a crossing.
You told me that this pinch and expand corresponds to, I was actually matrix algebra.
Mm-hmm.
And then I plug in any rank one out of the
Mm-hmm.
I have lots of choices for that.
Yes.
I'm not sure what exactly you mean, correct. Like you don't want to demand that it's a variant of your symmetric group or something like that.
So when
Like literally any idempotent.
I could make it work with any idempotent. So it's sort of, right, I mean, I'll get the same algebra.
I guess that's true, because some idempotents will like, kill some of the strands off, and
I mean, it's a matrix algebra, right? Like,
it's not a mystery matrix, it's a matrix algebra with a specific.
yeah, no, I understand. And the diagrammatics I want to use are fixing a particular choice of idempotent.
You have some choice of idempotent.
But all idempotents in a matrix algebra, all primitive idempotents in a matrix algebra are isomorphic.
The matrix algebra with specific actions, what is isomorphic matter?
Yeah.
But in any case, you have one in mind.
Yes, I have one in mind.
Name of an idempotent.
Yes. Yes.
And here you're saying that particular idempotent for NH2 is this guy.
Yeah.
And it's somehow possible to prove this theorem without knowing this actually.
Sure. Yeah, I mean, this is just like every one of these pictures corresponds to an actual homology class. And you can show that you get every homology class that shows up in that BFN picture this way, and that they satisfy the relations I had on the previous page. And that's essentially all you need to check. Yeah.
When you want to do the algebra composition
Mm-hmm.
and to somehow compose this pitching together,
Which is why I have this picture.
It's a completely old conversation. Like, you know that all.
yeah, the question I was wondering, like, if we use some of this idempotent, would you get the constants or not?
Okay, I was trying to get around this because I don't think it's actually an extremely important point. But so you will get the right relations if whenever you pinch things together, you replace that with do a half twist. And whenever you split things apart, you then do the idempotent that comes from that half twist. Okay, so when I draw a picture with a pinch or a split in it, if you wanted to actually calculate, you would replace the pinch and the split by these diagrams. And this in particular has the relation that if I pinch and then split, I get the half twist.
No, I mean, you guys went in this direction, so let me understand it. So, why do these two compose to this
Stick on the right.
This is applying the relations from the previous page. So it's a slightly long calculation. Maybe a good way to think about this is the Nil-Hecke algebra has a representation on polynomials, where a crossing acts by a BGG de Mazur operator, divided difference operator, and the dots act by polynomials. So this, you can check in this that this is an idempotent which projects to the invariant polynomials. And this is the longest divided difference operator. So this is just doing some calculation with divided difference operators. And if I wanted to, I could have put the product of the positive roots down there, but you know. Okay. So what I was trying to get to was this example of T star of CPN as a Coulomb bridge. So this should be the easiest case possible. So how should we think about this? Well, the affine guy, it's polynomial satisfying some algebraic equations. So, sorry, matrices satisfying some algebraic equations. So in particular, there are functions on this space which are take the actual matrix coefficients. And in fact, those generate the space of polynomial functions, and they just have to satisfy some relations. Yeah.
You explain that functions on this space
Yeah.
are diagrams of some kind
Yeah.
with some digits.
Yeah.
No difference. I understand.
Yeah.
Now go to the next one.
Yeah. And
What is the statement here?
so one special case of this theorem, so this is the moment map image. This, I'll just remind you, this is matrices n by n, whose square is 0, and whose rank is less than or equal to 1. So this is the image under the moment map of T star CPN. That's the thing that T star CPN resolves. So this is a subvariety of matrices. So in particular, the polynomial functions on it are generated as an algebra by the matrix coefficients. So the kind of natural way to try to describe this isomorphism is to try to find what are the diagrams that correspond to the matrix coefficients. And, oh, shoot. Oops, I think I meant to fix this diagram, and then it slipped my notice that I hadn't. Those were supposed to wrap the other way, because otherwise I would have just had the same diagram twice. I'm sorry about that. Okay. So, assertion, this is the way to do it. I have the matrix coefficient corresponding to the ith row and the jth column. And what do? I grab all strands between the ith and the j minus first, and I pull them around the cylinder. And whether it's the ith row and the jth column or the other way around is just which way around the cylinder do I wrap.
But these guys will in general satisfy some non-commutative algebra. How are these functions on the space?
Yeah, I'm thinking of matrices as an affine variety.
No, I think you asked a different question, which is, I think the question is, maybe I'm saying the wrong thing, but I think the question is, have you guys looked at this? And I look at your definition of this as a space of functions. It would not be obvious from that definition that what you define is something commutative. Is that true?
It's not obvious. Yeah, it's a surprising non-trivial fact that this algebra is commutative. There's a good sort of geometric explanation in BFN of why it's commutative. I mean, somehow the idea is this has to do with
I see. You're saying that I should have already been surprised that the BFN definition of the Coulomb branch was an algebra of functions on something in the first place.
yes.
As a convolution algebra, it had every right to be non-commutative.
Well, except that there's a good geometric reason that it isn't.
The ravioli nonsense, or like?
Yeah, I mean,
Okay, but I mean, in terms of like the algebraic geometry you're actually writing.
yes, right. No, I agree. Yeah.
But is there some shadow of this explanation in your pictures, or can you prove just mathematics that what you put down is?
No, I mean, I don't know an easy way to do it. Maybe it's not too bad, but yeah, it isn't something that just leaps off the page.
Is that your question?
Yeah, exactly.
No, it's a good point. I mean, so when you're thinking about it in terms of raviolos, like the composition has to do with, like, you know, if you're cooking ravioli in a pot, 2 of them can get stuck together, right? And this 2 ravioli stuck together, that's sort of the multiplication. You know, you pull back by the maps of peeling the 2 ravioli off, and then you push forward by the map of mixing the filling. And, you know, somehow, like, the commutativity of this multiplication has to do with the fact that, like, you know, somehow if you were able to move the fillings of the ravioli inside the outside, you could swap their places. This is like why pi 2 is commutative.
Do you ever do any actual cooking of that?
Yes, and I've had issues with ravioli getting stuck together. Now, I agree the part where you flip the fillings without disturbing the outside of the casing would be very tricky, but, you know, this is theoretical physics. Maybe. So, you know, somehow, like, the moral answer is, well, if you had that, you should be able to make it like 2 ravioli between a single sheet, and then you could move the 2 things past each other, which you can't do algebra geometrically, but you can wave your hands and say, yeah, okay.
There's no shadow of this in the diagram.
Not obviously, no. You would hope that somehow, like, you could kind of draw the 2 diagrams on the cylinder together and then kind of resolve them one way or resolve them the other way, but there's no obvious way to do that. Yeah?
Can I go to the next page where you do P?
Yes.
How do you come up with this interpretation? What defines such?
How would I guess that these are the right things?
I don't understand how it connects to the geometry.
Okay, so one good answer is that the matrices, thought of as a usual affine variety, have a scaling action of C star on them. And that grades the functions on the matrices. And of course, that preserves this subspace, the square 0 things with rank no more than 1. So the functions on that affine variety have a grading. And that grading you can read off from the pictures. And so these diagrams, you could guess that these were the right things because these are all the diagrams with degree 2. Right? So if you were going to try to find the matrix coefficients as functions on this guy, how would you find them? They're the things that scale with weight 1 under the scaling action. And actually, on which, I mean, for weird conventional reasons, you would you want to use the square of the usual scaling. So the matrix coefficients have degree 2, and those are the only functions that have degree 2, right? They span the space of linear functions. So you can actually guess that this has to be right just based on the fact that these are the only diagrams that have the right degree. You can then explicitly check that they do the right thing. The other thing that can be useful, right, is there's a Poisson structure on things. So you can check that the Poisson structure gives you the Lie algebra structure of GLN. On these functions. And I didn't have very much room, so I just wrote this kind of abbreviated thing. The diagonal matrices come from dots. And the correct thing is that the diagonal entry in row I and column I goes to take the diagram where all the strands are straight, put a dot on the I minus first strand, and then subtract putting a dot on the I strand. Sorry? Yes. Hopefully I got that right. I have to admit, I didn't check this maybe as carefully as I should have. But yeah, I mean, that should have to do with EI is the commutator of EIJ and EJI. Yeah, well, take that statement, but it's sort of, and it's possible I remembered this wrong. I don't absolutely swear, but it's definitely the dots. I thought that was right. Okay, well, we'll see. Okay. Any other questions? So this is kind of the first interesting non-trivial example. Whew. Okay, well, what if we wanted the Grassmannian 2, 4? So this is, I look at matrices, A squared equals 0, but now I allow the rank of A to be 2. And they're 4 by 4 matrices. So I do a little calculation with Hanani-Witten. I mean, I talked about the general case before. And I have the 2 blue strands on the outside, 2 D3s and 4 D5s. And I do a Hanani-Witten transition where I move the 2 blues to the middle. And what do I find? I have 1 D3 on the 2 outside guys and then 2 in the middle. So I get this quiver gauge theory. So I have 2 red strands with label 2, 2 black strands with label 2, and 1 black strand each with label 1 and 3. And now if I want something in the Coulomb branch, I have to pinch down my 2s together. So now the pinching actually matters.
There's the different item you could have done, the more obvious one, which would be like the 2, 1, 3, 2 ordering.
Sure.
That would work for you?
Yes, yes.
And
So,
do you have to pinch them still because the 1 and 3 separate the 2?
oh, sorry, you said, no, you shouldn't do that one.
Why not?
Because the
That
2s
doesn't
aren't
matter
together.
which one- But you said it doesn't matter which one you take.
No. You were saying which item was.
Yeah, so I could move this.
No.
Yeah, but no, that guy doesn't work.
Why not?
Because the 2s have to be together.
Let me just say what he had said. I'll explain to you which thing what he said. You have to take a guy where all the ones in the same level together. And then having done that, you get the action of a nil-Hecke algebra on things at the same level. And then you use an idempotent of the nil-Hecke algebra. And what he said was, you can any idempotent of that nil-Hecke algebra. You always have to put all the same ones together.
So you said that the object I told you about did not correspond to a line bundle on X or something?
The guy you told me about, that actually, so that corresponds to a rank 2 bundle, which is actually the sum of 2 line bundles, I think. Oh no, maybe that one. No, that's an indecomposable degree rank 2 bundle.
Anyway,
So no, it really does matter. It's really important that the 2s are together. It's because I want the trivial line, right? And so I have to have the 2s next to each other, and I'll get a trivial line coupled with a P1, and then pinching them gets rid of the P1.
Okay, I have a question. How do you came up? Is this an experimental discovery?
Okay, wait.
Came up with this, like, how to match the diagrams coordinates.
Okay, so here, right, I told you one example of how diagrams match with coordinates. So again, I just have these functions. So, I mean, there's sort of 2 answers. So one answer is you can go read a bunch of papers about the connections between finite W algebras and Yangians and all of these guys. And eventually you could trace through and it would just tell you the answer.
What you said different from, I don't understand how any of that plugs into the things you said so far. Let me just ask that. So are you saying that you have proved a theorem that identifies various items with classes in this homology? And BFN have proved a theorem which says that.
Sorry, what was that name?
So
Yes?
And then some other people have proved a theorem that say that convolution algebra is this thing.
Yeah, Nakajima and Tatayama.
Okay, those guys. Then you just read those two papers together and then discover which function.
So I would say that those two papers together, I mean, it's possible that you could somehow extract from those two papers together what the answer was, but it would be very, very hard. I think there is kind of a more principled way to do this by, basically there's a literature about some of these isomorphisms after you quantize. But the other way you could come up with this is, again, you could look for the diagrams of the lowest degree.
Which degree?
So the degree that corresponds to the C star action, I do have it written. I sort of realized I should add it, but I think I added it relatively late. Yeah, it's this degree.
I don't understand why is it it's impossible to do the thing which I said.
Because if you just read Nakajima and Tatayama's paper, like, then you have to apply, they define an isomorphism corresponding to the Hanani-Witten transition, and you have to apply that isomorphism a bunch of times. Maybe in the 2-4 case, it wouldn't be too bad, and you could manage.
It's in that isomorphism.
Yeah, and I mean, I think it's much easier to find by hand the diagrams that have lowest degree. So yes, I mean, like somehow you could trace through that paper to do to get what you want. I think it would be pretty hard. So this grading, this corresponds to the homological grading in BFN. And so it corresponds to the scaling C star action on, on nilpotent orbits, but doubled because you want degree 2 on the symplectic form. And so linear functions on matrices will correspond to degree 2 elements. So what Nakajima proves, right? He proves that this Coulomb branch of this theory is, right? He proves that there are different descriptions of bow varieties that give you isomorphic varieties. And exactly that there's an isomorphism between those bow varieties every time you do a Hanani-Witten transition, right? So there's a bow variety which is obviously T star of the Grassmannian, which corresponds to this picture. And then in order to get the description in terms of Coulomb branches, you have to do a bunch of Hanani-Witten transitions. And so you have to apply the isomorphism that Nakajima uses for each of those. And I mean, maybe I'm making it sound harder than it is, but it's sort of not a totally trivial thing.
But that would help you. But you still have to run this through some giant machine that starts with the right-hand picture and produces coordinates, right?
Yeah, well, I mean,
the left-hand side will give you coordinates by definition, but the right-hand side, you have to.
Yeah, I start with this. I have to go into BFN world, and BFN world, and these theorems about the KLR algebra tells me I should look at pictures like this, and there should be some distinguished pictures like this that give me the coordinates, right? And in general, so it's sort of like the projective space picture. So what does Eij with I less than or equal to j correspond to? It's grab one strand with label I, one with label I plus 1, etc., up to j minus 1, and loop all of those around the cylinder once.
There can't be some good general answer, right? This is, I mean, here you just have Grassmannian, it's not so bad, but I mean, in general, these things are done.
I mean, so roughly this answer should work for all of the type A nilpotent orbits written as Coulomb branches. So I don't know if you consider that general or not general, right? So for other cases, well, yeah, there isn't a kind of nice, obvious embedding of them in matrices like that.
Maybe you ask a different version of my question, which is, never mind all these naughty written moves, but what are the first step? Is it explicit how this kind of this BFN or whatever algebra is related to this Turkish algebra, the algebra which describes Turkish property?
That's a good question. I would want to look at Nakajima's paper again before I answer that.
It's relatively explicit, at least it's simple enough. I'd be much more afraid of that than I would about all these things.
No, like, if you're interested in Coulomb branch or whatever, that's not hard. You can try to write down the part, as long as you have a case acting to it, like Coulomb branch. We are functioning. We're doing that for a month.
All right, any questions? Okay. All right, but that's just the affine variety. I'm supposed to get a projective variety. If I want to get a projective variety, well, I don't just need functions, I also need sections of a line bundle, powers of a line bundle. The kind of easy way to say this is that I extend my KLR algebra by, instead of saying that my red strands are vertical, I say that they wrap, each one of them is assigned a number of times to wrap around the cylinder. And my assignment I capture in an element of z to the L. So L is the number of red strands, total number of red strands. So this gives me a graded ring, where I just do stacking for composition again.
I don't understand. When you say, is it a formal number, or you actually draw a picture where the red strand goes around that?
I actually draw a picture where the red strand goes around that many times, like this.
So the red strands intersect.
Yes.
And you worry about the red strands intersect?
No, that's okay. That's okay. The only relation I need is that I can resolve a bygone of red strands without, doing anything unusual. But since I'm going to be taking a proj, I'm going to be taking positive multiples of the same winding number. So I'm never actually going to encounter the situation where I wind a red strand one way and then wind it back the other way. Okay, so this is a graded ring. I can think of that as giving me a U1 action, U1 to the L action on spec of this bigger ring. And I can take a GIT quotient. And I know that's kind of fancy, that's just to make it sound easy. What that means is I pick an M, I look at all the positive multiples of M. So I choose a number of times for each strand to wind around. If I want to be generic, they should all be different. And I look at them winding around that many times, twice that number of times, 3 times that number of times, 4 times that number of times. That's a graded ring where there's another grading in the picture, which is this K. And I take proj of that graded ring, which basically means I build the quasi-projective variety where I have a line bundle O of 1, and the sections of its kth tensor power is this guy where the red strands wrap around K times M many times. So again, this is just, you go read BFN's Lines on Coulomb Branches paper. They tell you what to do, and this is what happens when you translate that into KLR world. So you can think of this as a symplectic reduction of the bigger algebra, where you add in the torus acting on the square nodes to your gauge group. So if I did that, That would mean letting the red strands wrap around any number of times I wanted and allowing dots on them. So I do a symplectic reduction, that kills the dots, and then I'm taking invariance as well.
No, you don't need that. What's the relationship between what's the resulting outcome for that?
Nothing.
Nothing, just the
Yeah.
compute.
Yeah. Yes. Yeah, and I mean that you would read that off from the BFN construction if you throw in, you know, that's because if you throw in the torus of the GW, there's no fundamentals for the GW, like bifundamentals for the GWs.
You should be able to do that. I mean, in fact, I think we did. No, the tensor was a line bundle on the B side. It is moving red functions around.
Yeah. Okay. Any questions? So this is just BFN. Tell me this is the partial resolution of Coulomb branch I should take. And I say, okay, I will take that partial resolution. All right. So what happens when I do this in the projective space case? Well, I know what I'm supposed to get. I'm supposed to get T star CPN minus 1. And again, I haven't written this out in great detail, but the sort of important thing is, well, O of 1 on T star CPN has a bunch of obvious functions that are the actual coordinates thought of as sections of that line bundle. And so there should be obvious diagrams that correspond to those. And indeed, there are. If I want xj, I just grab the first j strands, they go around, and the other ones stay. So it's often, quite often, the easiest way to think about these sort of constructions is my red strands are going around, and I think about which red strand do guys follow, right? So by this discussion we had earlier, I'm trying to minimize the degree of my diagram, right? So these guys can be distinguished from the space of sections of O of 1 on T star CPN by they're the, or n minus 1, I should say, by they're the lowest degree functions for the C star action.
Why does your diagrammatics know the names of the coordinates? Yeah, that's always one question.
Well, I chose an isomorphism between some diagrams and the Lie algebra GLN before, and GLN knows the names of the coordinates. I mean, I think another way to say this is, well, these diagrams here for the different J span the lowest degree sections of O of 1.
Yes, I agree.
So that has to be the dual of the projective.
But
Yeah.
you don't know the span of them. You know the individual one. That's what I was confused about. I think I'm not good at explaining the answer.
Okay. Yeah. Yeah, I mean,
This time around, claiming that the mirror symmetry, you can deduce the coordinates. I don't remember exactly what he said, but he said you can mirror symmetry like from the A side and use the coordinates on the B side, but that's not really what he's doing.
Well, sometimes that's true, but I mean, a different way to complain about this is to say that you must have at some point destroyed the full GLN action on this projective space.
yes. Yes, that is one of the upsetting things that happened.
And you destroyed that when you showed this isomorphism?
Yeah, well, that might have been the problem from the start.
Whenever anything is presented as a Coulomb red, it's always kind of like big non-abelian symmetries that act on it look kind of accidental.
Yeah, I mean, like you can get that action back, but there's some work involved. And yeah, actually, one of the things that's been annoying for us is we haven't. I mean, this is a GLN equivariant vector bundle, and so we should be able to sort of get that back, and we've had some trouble with it. Okay, but you can guess that these have to be the right diagrams because, again, they have lowest degree. All right, any other questions about this? Okay. So what about T star of GR 4? So if I look at the sections of O of 1 on the Grassmannian, then that's a copy of the second wedge power of C4, right? That comes from the Plücker embedding. So again, I should look at the lowest degree elements of this space of sections of O of 1, and I should find a copy of C2 of C4, wedge 2 of C4. And like in the projective space case, I can kind of guess based on what the weights are supposed to be. All right, so this is the highest weight vector of wedge 2 of C4. And then I can get all these other ones by doing lowerings. And every time I do a lowering, I wrap one more strand around the cylinder in the positive direction. So here, like when I lower from X1 wedge X2 to X1 wedge X3, I have to wrap one more strand with label 2 around. I'm lowering from a 2 to a 3. That means I have to add a wrapping of a 2. Here I'm lowering from a 1 to a 2, so I add in one more wrapping of a strand with label 1. And you'll find here exactly the ones where I have the ability to do that without changing the degree correspond to the legal lowering operators in wedge 2 of C4. So here, instead of lowering the 1 to a 2, I lowered the 3 to a 4. And now, after doing one of those, I can lower the other one. And then finally, I have one last guy I'm allowed to lower.
Is it important that you place your black strand in your order of 1, 2, 3, 5?
No, but it's important that I fixed the order and use the same one on the top and the bottom.
Yeah, of course.
No, exactly the same pictures would hold if I swapped 1 and 2. And I mean, one thing worth noting is if I swap the order of these, I never end up changing the degree, right? It's always I trade a crossing here for a crossing here.
So the last issue has 2 strands.
Yes, so in these ones where the black strand never splits, that's sort of thickness 2. If you want to be very pedantic about it, there's this relation that if I split, gosh darn it. If I split and have a dot, that corresponds to just a thick strand. So yeah, somehow the first one and the last one, the 2's never split. All right, any other questions? All right, so why was I doing this? I mean, okay, hopefully some of you were interested in the question of how to think about this resolution anyways. But I wanted to understand a particular thing about it. I wanted to understand the category of coherent sheaves on that resolution. And you could say, well, you know, it's proj of a ring, so you can understand coherent sheaves in terms of modules over that ring. It's true, it's true. It's not the category of modules over the ring, though. It's category of modules over the ring modulo the ones of bounded degree. So there is this kind of annoying thing that there are some modules over that ring that correspond to the trivial coherent sheaf. So I would rather have a single ring that really describes things. And one way I can do that is to have what's called a tilting generator. So this is a vector bundle that captures the whole category of coherent sheaves on my variety. So the kind of easy way to say this is taking Hom with this vector bundle induces an equivalence of derived categories from dB Koch to dB of modules over the endomorphisms. And I guess this parenthesis is in the wrong place. All right. So this is a vector bundle which kind of captures the whole structure of the category of coherent sheaves. There's a nice way to say this, which is the endomorphisms of this tilting bundle is what's called a non-commutative Crepin resolution of singularities of the affine guy. Which I think I was missing a 0 there.
What was our circle?
That was the cylindrical KLRW algebra. So yeah, before when I was talking about the Coulomb branch, I was just taking one piece of it. I was taking one idempotent and taking that bit of it. But if I want the whole category of coherent sheaves, I want to take the whole cylindrical KLRW algebra with all the other idempotents in it. No, this applies to any of the quiver gauge theories that came from this Hanani-Witten picture. In general, a version of this theorem works whenever this MM is a symplectic resolution of singularities. That's kind of the key thing is there are actually relatively few theories where we know that happens, but for example, in all the abelian ones.
When you say something is a non-commutative Crepin resolution, you give me like a map of grades, right?
So I mean, what that means is, okay, so there is a formal definition. The sort of important thing is coherent sheaves on the thing you're resolving is a quotient category of this. And it sort of behaves like the coherent sheaves on a Crepin resolution of singularities homologically. A map of rings from, sorry, you're asking if I have a commutative ring and I have a non-commutative Crepin resolution of singularities, usually what you would expect is that that commutative ring is gotten from the non-commutative one like this for some particular idempotent.
How is it supposed to be related also to the center of R, or maybe a subalgebra of R? Or R is an algebra of R?
No, I mean, this is right. So if I had a Crepin resolution of singularities, how would I get the functions downstairs? It would be the endomorphisms of the structure sheaf upstairs. Right? So there would be a particular object in the category that it was the endomorphisms of.
That's true, but it's also true that it's the Hopf homology. Like the zero Hopf homology. If you have the endomorphism of variety or projection over affine variety, the tilting bundle of it.
Yeah.
Then the coordinate ring of the affine variety sits inside the endomorphism algebra of the tilting bundle.
Yes, that is true. Yeah, no, I understand the point you're making.
That doesn't mean that relationship's false. They might both be true.
They might both be true, but I think this is the one that people usually ask for in the definition of non-commutative Crepin resolution.
Like matrix algebra, right? Like you have n by n matrices. Like you take like trivial idempotent. And it's both true that the field is this thing and also the center of the matrix.
Yes.
Okay. I think it's that kind of situation.
I would want to double check before I made any assertions, but I believe this is the one you usually see as an assumption.
I think the argument is one that must be true. That somehow it must be enough. But usually that's the definition. It's the yeah. You can take it like that definition, whatever, in algebra over A, over the singular thing. He's upstairs, right? And we can fuck him up and ask him. We show this up.
All right.
Are zero includes the things guys or doesn't?
It doesn't matter, actually. It's the same up to Morita equivalence.
That's one question.
Yeah, of course.
So,
You can ask more than one.
So I'm just new to actually, I'm new to this crossing of the red strands. I know it exists, but I never thought about those or work with those. So if you give me say T star P1, you ask me
represent the object, say, O1 of this structure one, I would call this equal to W, and the division maybe my next strand in a certain way. Right. This structure one, the circle is two red dots.
Mm-hmm.
It's a make a choice, I say, put a like dot here, that's O0, that's not a like, it's O1. I do that. Right? So arbitrary choice. But here I'm telling me, no, I should do something different. I should let my red strands go across.
Yeah. So let me talk a little bit about that case. So, right, you know, how would you? So in I think I actually do have something. I remember writing this down. Yeah. Right. So what this is telling me. Yeah, let me actually come back to this. Let me finish what I.
Just imagine the picture, right? You start taking one of the functors around, you're going to take O0 to O1, and then O1 is going to go to O2, and that O2 is not exactly.
Well, let me finish the statement. And yeah, well, we'll come back to that example because I think it actually is important. Okay, so yeah, I was just saying there is a tilting generator on this guy, and its endomorphisms are this KLRW algebra. So how do we construct this guy? Oh, this was just saying that this one says over C. I conject the bundle is actually defined over Z. So I think it gives us a tilting bundle over any field, but the bundle is defined over Z, and the theorem says over any characteristic 0 field, or characteristic P sufficiently large enough, it gives you a tilting generator. Conjecture, you don't need to say large enough.
I mean, before, how you said that if isomorphism wasn't even supposed to be true at all, just at all, P except for some particular ones.
So I mean, I have a vector bundle, which is defined for over all fields.
I'm just trying to compare this to the statement that we began the lecture
With the Bezrikov-Koulomb? Yeah, I mean, it's a similar sort of story where you prove some fact about like.
I understand, but you said about that story that it was not expected to be true for all, just all P, but some very specific ones.
Yes, because somehow there's some obvious problem with the universal enveloping algebra at small p that I can avoid using this tilting generator. So, you know, somehow this guy isn't quite the one from doing quantization in small characteristic p. There's some problem with that where there just aren't enough elements of fp. And you can sort of formally get around that obvious problem. And the conjecture is that was actually the only problem. Okay. So to talk about the sheaves we want to get, I'm going to use that there are these idempotents in the KLR algebra. So just E, if I write a sequence of red and black numbers, that means take the straight lines, label red and black in that order with those labels in that order. So here I would, you know, this is E of 2, 2, 3, 1, 2, 2. Okay, great. So it's just useful to have a notation for that guy. Okay, so we can take the KLRW algebra. We can let the red strands run around the cylinder any way we want. That's what putting that tilde there means. We can multiply on the right by our idempotent and get a right module over the Coulomb range. The idempotent E sub C, the one that cuts down to the Coulomb range.
The squishy one? Or
yeah, the squishy one, the pinchy one. So that's a right module over the Coulomb branch where I've done the pinchies. and it's a left module over the KLRW algebra. Okay, so by GIT quotient, I get a coherent sheaf on this partial resolution from this module. Which means that, what am I doing? I'm looking at the coherent sheaf where the sections after tensoring with a big power of O of k is diagrams in the KLRW algebra with the pinchy at the bottom and where the red strands go around k times m many times. All right? That's the KLRW algebra, but you let the red strands go around.
So they're peak of particular direction, correct?
No, that's just all possible things. But then putting the k times m there means I've kind of picked a particular direction. Right? So I need something where I can multiply on one side by these diagrams where I've done pinch at the top and the bottom, and the red strands go around. Right? So my diagrams have to also have red strands going around. And the number of times they go around tells me which OK I'm looking at.
Is the point that in your previous slide, you explained that there exists some tilting module, and you didn't tell us how to construct it.
Yes.
And what this theorem is saying is that, okay, you have some secret way of constructing it, but in fact it's this.
I mean, I would say this is the construction of it. And then secretly, you know, you want to prove that it's the same as Bezirkov-Nikov and Kaledin's for large P.
What does it mean that it's obtained by GIT quotient? Because those are coming out related ones, really some sort of version of GIT.
Yeah, I mean, what I'm telling you is, I mean, I define this GIT, the partial resolution, as a GIT quotient. So one natural way to get a coherent sheaf on it is to define an equivariant coherent sheaf on the guy I did before. And of course, that's relatively easy because the guy I started with was affine. So I just need to tell you a module over this Coulomb branch algebra, right? And one natural way to get that module is, well, the Coulomb branch algebra comes from taking this bigger algebra and multiplying by an idempotent. So I multiply by that idempotent on one side, and I get a module over it. And I can turn that into a coherent sheaf. Now, right, you know, this description is just explicitly saying, what do I mean by the sheaf I got on the GIT quotient from an equivariant sheaf upstairs, right? It's saying, I'm telling you what, right? T is uniquely characterized by saying the sections of T tensored with O of k is this space for k large.
Basically what's going on here is we're using the fact that this resolved Coulomb branch is really a quotient of a different Coulomb branch. And
Yeah.
that Coulomb branch is also affine, so we should hit.
Yeah.
And we use that.
Yeah. And just whenever I have an algebra, a commutative algebra that comes this way, I have a natural module, which is just RE, and I can think about the coherent sheaf corresponding to that. And I do that construction for the tilde guy, and then I do GIT quotient.
Is this just for the Grassmannian, or are you putting this general statement?
I mean, this is, so,
Everything there is holds in general, I mean,
so
in general.
the definition of this sheaf makes sense for any Coulomb branch. Just as, you know, there's a coherent sheaf that has this property, you know, whose sections are this guy.
But T was your tilting guy.
Yeah, so the theorem that it's tilting, that's true if this M super M is a symplectic resolution of singularities, which of course it usually isn't. So I need to,
It isn't.
I mean, for a random matter and random gauge group, no, it usually won't be.
What's the definition of that?
I mean, it's, right, so the physical way to say this,
It's like if you take your quiver and then gauge the torus in the matter flavor symmetry. That gives you a bigger Coulomb branch, and you can can
Oh,
show that the
yeah.
Coulomb branch for the ungauged one is the symplectic reduction of the big one. And then the point is that now you can turn on a real mass before doing the reduction.
Yeah.
And if you know, fingers crossed, it might resolve the whole thing. But the issue is that, like, for random quivers, you really don't.
Yeah. But for linear and cyclic quivers, it does work. So for the ones that, you know, come from this 2B string theory, then it's okay.
Can you show that? Sorry, yeah. I thought it's true that it's expected that there's supposed to be some correspondence between when it's not a full resolution and when, like, you don't have isolated fixed locus and non-commutative varieties, right?
I mean, that's supposed to be the sort of some S-dual condition.
Yeah. So, is it known with the definition that BFN gives that this works out, or it's just random questions?
I don't know.
Okay.
I would want to think about that. Probably not, but I'm not absolutely sure.
And when you say, is this some type of resolution, what you mean is, like, we had such a question, is that something smooth? Is that
Yes. Right, it's always a, well, it's always a symplectic variety. And the question is just, is it smooth or not?
So you want to consider all such idempotents?
Yes. The point is, every such idempotent gives me a summand. Right, so the kind of natural thing to do, oh, I should have put that on the other side, doesn't matter.
You're just presenting it in a different way, you want to say it.
Yeah.
Yeah.
So right, what this means is, you know, I look at this picture, I've got the pinchy guy on the bottom, and then I fix what the idempotent on the top is. And that gives me a coherent sheaf. Okay, so what tilting generator do we get? How would we check this? So let's talk about P1 first. So P1, you know, this corresponds to our trusty 2, 1. So 2 red strands, 1 black strand, all with the same label. And what I want to think about is, oh, I said top, I switched top and bottom, sorry. So the Coulomb branch stuff is acting at the top. That's giving me my coherent sheaf structure. And if I fix the idempotent at the bottom, that gives me a summand of my tilting bundle. So what are these pictures? So this is a section of one of the summands that shows that that summand is the structure sheaf. So if I just take the E on here, then I just get the algebra back. I get the algebra as a module over itself. That gives me the structure sheaf. What's this picture? So this is a section of the summand of my tilting bundle, tensored with O of 1. And it's a section that proves after I tensor with O of 1, I'm isomorphic to the structure sheaf. So before that, I must have been O of minus 1. Okay, so it proves I have a map to O of minus 1. So I have to check that that map is an isomorphism. And you're right, that doing that very carefully requires a bit more work. What would I do? I would think about what happened as I did more and more wrapping around, and I would see that I was getting, yeah, right? So somehow the point is this guy. So why do I believe that this is an isomorphism? Because it's the only thing I can do that doesn't cross any red strands. And if I put in another wrapping around, I'll be forced to cross one red strand, and I'll be able to choose which red strand do I cross. So I'll have 2 choices. That looks like sections of O of 1. If I do another wrap, I'll have to cross 2 red strands, and then I have to decide, do I cross this, this one twice, the 2 different ones, or this one twice, and that will look like sections of O of 2. And I mean, I can probably do a little better than that. I could probably define an inverse to this guy that would give me an isomorphism. But, so yeah, I mean, okay, are there any questions about this? So you had this discussion about if I put the guy on the other side, right? That's what I'm doing here. I'm starting it on the other side. So here it corresponds to O of minus 1. But of course, I made a choice about what n is. And I could have made a different choice. So I could have made m minus 1, 0 instead of 1, 0. And then what would have happened? Well, my strand would wrap around the other way. And now, rather than having a path that crosses 0 red strands, I have a path that crosses 2 red strands. And it's forced to do that. So here I actually get O of 1 instead of O of minus 1. And that's just kind of, you know, you have to make some choice.
Explain to me, like, what is the rule about how many strands it is? Like, why can't I send it around the other way?
Okay, so I mean, I'm choosing a resolution, and that involves choosing an m.
No, I understand that. Just about this diagram. You're saying once I draw the red strands,
Yeah.
there's only one way to black strand. Why is that?
No. No, the black has to cross 2 reds. I didn't want to draw them all because it will just get kind of horrible, but right, I can also,
Oh, you're saying there's lots of them?
yes,
You can count how many.
I can go around like this, or I can go around like this. Oh, sorry, no.
And you're supposed to draw every such picture and then pose the relations where they're equal.
Yeah.
The dimension of some constants. And from that you extrapolate.
Yeah, and the easy way to do it is to look at the lowest degree ones, right? Because that's telling you sections on the 0 section, and there are finitely many of them. So here, right, I tensored with O of 1, and I'm seeing 3 of those. If I hadn't tensored with O of 1, I would see 2 of them.
So the first guy, and its analogs will always correspond to like just a trivial vector bundle.
Yeah, the idempotent that gave me the Coulomb branch in the first place gives me a trivial vector bundle.
And then you're somehow saying that by using these monodromies in a clever way, you can generate all the other components. And by keeping track of what monodromies were, you'll figure out like what are the trunk classes of the other components, something of that sort.
I mean, that's maybe one way to think about it. You know, here I'm trying to do things very concretely. So, like, how do you figure out what coherent sheaf you have on P1, right?
So we've decided we have a trivial vector bundle, and then you're looking at its harms to other components. No, I'm not that.
Okay, so every arrangement down at the bottom corresponds to a summand of the tilting bundle. So there's a summand that corresponds to this guy, and that's always the trivial. There's a summand that corresponds to this guy, and I want to know, what is it?
Right.
And the way I try to figure that out is well, you could say in general, like I look at the space of sections of its tensor powers with, you know, OK, right? In this case, what I'm doing is, you know, I'm just illustrating, if I tensor with O of 1, I get the sections I expect for O of 2. If I tensor with O of 2, I'll get the sections I expect for O of 3, right? And then that tells me, oh, it must have been O of 1 to start with. Let me just say, right, if I had started here, right, then if I start here, then I have 2 obvious sections. I can go this way, or I can go this way. But I can't tell the difference between O of 1 and O of minus 1 just from those, right? Because O of minus 1 also has 2 sections in lowest degree that come from the 2, So I have to start looking at tensoring with higher things and saying, well, what happens when I tensor with O of 1? If I had 2 sections in lowest degree, then I tensor with O of 1, and I get 1 section in lowest degree, that tells me I must have been O of minus 1. If I've,
I'm not sure I really read you that can tell. I don't mean less. I'm not sure you can possibly know what A is based on this discussion.
well, yeah, what I just illustrated in this case is that there are 2 different possibilities for P1.
How do you know what A is? Because as far as I can tell, you've done, taken one of the components, taken off from that component to itself, and concluded that that was A.
No. I'm looking at sections of this guy.
Well, how is it sections? It's sections that's half of O. How do you know who O was?
But I mean, this guy essentially by definition is O.
No, but you don't even define who O is. I mean, I'm sorry, that's what I don't understand.
No, I mean, in this example, you can see how you could do it. If you just think about on the A side, right?
I want to see my question.
The question is how you're going to repeat this.
I mean, this guy's by definition, I take the ring as a module over itself, and I take the coherent sheaf on proj that gives me. That's by definition the structure sheaf on proj. Whereas this is some other module over the projective coordinate ring, and I want to find out what the corresponding coherent sheaf is. And I can't do that just by looking at the degree 0 part. I have to look higher.
But you claim that there's a systematic procedure that by tensoring by line bundles, you can always run this algorithm.
Yeah, I mean, on P1, that's the easy way to do it. There's another way to do it, which, I mean, I feel free to tell me that you guys want to go home. But there's another way to do this, which is to actually break things up into patches and look at the transition functions.
No, but certainly the T-star for this.
On P1, it's kind of easier to just tensor with O of 1, but I think in other cases, it will be kind of easier to use the patches. Yeah.
Oh, it will.
This is so unrelated. You're doing GIT, right?
Yeah.
You're choosing the co-factor,
Yeah.
factor is N. I was able to do like the walk crossing change, like chambers.
Mm-hmm.
I'm able to do that using the diagrams.
Yeah, not obviously. Yeah. Okay, so what about higher values of n? So this is actually where this sort of A comes into play. So I know that I have a sum of line bundles, and I know that it has to be a tilting generator on T star CPN minus 1. And so the only possibility is that it's a sum of n plus 1 consecutive ones. No, n consecutive ones, sorry. It's so hard to get off.
No,
Yeah.
I know that that's the answer, but I decided that he knows from NIW.
No, he's not saying that. He's saying he knows he has a tilting object, and he knows what tilting objects could possibly be. And I was trying to figure out which tilting object.
Yeah, well, and a tilting generator, right? So tilting object tells me it can't be more than n apart. And then the fact that it's a generator tells me I have to have all the ones in between.
Are you using your knowledge of algebraic geometry to do that?
Yes, I am using my knowledge of algebraic geometry to say this must be the answer. And so how do I see that that's the answer I get? Ones that are sums of line bundles are.
Right, okay, yeah.
And I know by construction that this guy is a sum of line bundles. On Pn, I mean, somehow the ranks of the summons are a function of the size of the vial group. And here the vial group has size 1. Okay, so great. So I look through these different idempotents, and then I basically do this business to check what line bundle on Pn do I get. So if I start with this 1, 1, 2, 2, That's the guy I was using to get the Coulomb branch algebra. So again, essentially by definition, that goes to the structure sheaf. And now I have this semi-random listing of other guys. The way you should think about this is when I start here, if I do a crossing of two things with adjacent labels, so a crossing that has degree 1, I'm going to change what the line bundle is. So again, I have to do a little computation to see whether the number attached to it goes up or down. But the thing to watch for is when do I do these crossings that have degree 1. So here, this is the isomorphism of O of 1 tensor, the guy for this idempotent, with the structure sheaf. And the thing to kind of watch for in here is, again, the following the red strands. So this 1 is trying to avoid crossing the red one because that would have degree 1. So when the red one sweeps around, this one follows it. And similarly, this 2 is trying to avoid crossing the red 2. And if I didn't have this 1 going around the cylinder, that would be impossible to do without one of the degree 1 crossings, right? I would either have to swap these guys or I would have to do one of these swaps. But adding in that 1 going around allows me to do this without any degree 1 crossings. Yeah.
Suppose I want to leave in my old form of straight red line.
Mm-hmm.
To the unwinding of the twisting of the red line.
Mm-hmm.
And after this morphism, I say the first picture of 2, 1, 1, 2, and that, of course, I have to twist my red line. I have to twist my, because I'm applying a global.
I don't think you can. I think it's genuinely, like, it really matters that this guy wraps around, right? I mean, the point is, this guy has degree 0. There's no interesting crossings in this picture, right? But I can only do that because the red line went around once, right? And so here, there's one guy that gives me O minus 2. And again, I'm doing this, the 1 wraps around twice, and this 1 avoids making a crossing with it, this 2 avoids making a crossing with the 2. And the 1 has to wrap around twice to be able to do that connection. And that's how you see it's O of minus 2. All right, cool. All right, so what about the cotangent bundle of the Grassmannian for 2 and 4? So this is a first non-projective space that kind of comes up in this picture. So whereas on T star CPN, you had summons of rank 1, they were all line bundles, now I can have summons of rank 2. That basically comes from the fact that I have the 2 2s, and there's kind of 2 different ways to connect them. All right. So on the Grassmannian, there's sort of a natural line bundle, not line bundle, rank 2 bundle called the tautological bundle. And the ample line bundle on the Grassmannian, the unique ample generator of the Picard group, is the second wedge power of the dual of that guy. So the only things I can get taking T and multiplying it by EI are the trivial bundle, O minus 1, and this is with one particular convention. There are 2 extensions between line bundles. So this is sort of the lowest degree extension that I can get between these guys. And then I get the tautological bundle and its perp bundle. No. Kapranov's collection is all Schur functors applied to tautological bundles. Kapranov's exceptional collection isn't tilting when you pull it back to T star of GR24. So we know it can't be Kapranov's.
you know the names of these things?
No, no, I had no idea that this extension was going to show up. I mean, this was really like, we did the computation, and then, you know, we were doing the transition functions, and it was like, oh, the transition functions are upper triangular. It's an extension of 2 line bundles. So no, I really have no idea how this is going to generalize. Yeah.
So what's the difference between the last 2 lines? It's like putting the
It's tensoring with O of 1.
oh. So W is the definition of one.
Yeah.
What is the mystery bundle? Like, is that a description?
Mystery what?
This B or W or whatever has some kind of more into the
I mean, you know,
one, yeah. Everything else is like kind of tautological objects. In some sense, but it's tautological.
yeah, it's the lowest, like the X1 has an action of C star coming from the scaling action, and there's a unique thing of lowest degree in X1, and that's what it is.
Sorry, I don't quite know what it means. You want to say that that guy is a cone over O, like the first guy? Over O,
Yeah,
over
yeah, it's an extension of these two. Yeah. And it's sort of, there is, so this extension, it splits if you restrict to the 0 fiber. I mean, again, we like explicitly calculated the transition functions, and the upper triangular part is like literally 0 on the Grassmannian. But you can compute X between these line bundles after you pull back to the cotangent bundle, and it's the lowest degree thing.
Does it have anything meaningful if we compare it to T star on the dual Grassmannian?
I mean, this is one of these things where,
It's like, does the last 2 lines become like the first 2 lines? Or because like T and C dual like looks like they will change?
I think what will happen, I mean, somehow, right, like basically what you're asking is, what if I have the strand wrap around the other direction? Right, somehow that's the, you know, the Grassmannian, the dual Grassmannian, it's doing the 2 different characters in the GIT reduction. And the answer is I sort of, we haven't carefully checked how the description is different if you do that. I mean, I irresponsibly guessing, I would guess that you just tensor with a line bundle, that it's the same up to tensoring with a line bundle. But
So they have IBM under.
no, I mean, and like, well, I mean that, like,
Let's not make that irresponsibly guess.
no, I'm fine with irresponsibly guessing.
The last 2. Yeah, no, I think that's obvious.
I mean, there are obvious operations you can do on tilting generators that also give you tilting generators. So actually, probably I'm taking the dual, right? The dual of a tilting generator is always a tilting generator. And I would suspect that's what happens, but now that I say that, I should carefully check that.
Some guys here are actually rearranged.
No, they're genuinely different. This is the perp of T, which is different from the dual of T. Right? Like, you can, these vector bundles end up being GL4 equivariant. So you can define them by looking at a representation of this guy. Right? And so there's a 2-dimensional representation of this block. There's its dual. There's a 2-dimensional representation of this block. There's its dual. Though now that I say that, they're not really that different. Okay. So now, having said that, probably actually the dual of this guy just differs from it by tensoring with a line bundle, and it's probably okay. Yeah.
You answered that before. So, what's the relation between the zero extension and the cotangent bundle? Like, between the 2, are you able to construct tilting bundle
Yes, the restriction of these guys should be a tilting bundle in the zero section, but the guy on the whole cotangent bundle won't be the pullback of that. Right, so you can't just get this guy by constructing a tilting generators on the bottom guy and then pulling back. Okay. So, I mean, obviously there are idempotents other than these. This is sort of a nice one. The way I got these.
In principle, you're supposed to take all those idempotents.
Yes.
We were just saying that you wrote them all down, and it turned out that they're all one of these.
Up to some like summon stuff. So I mean, somehow it would have been better to say like all of the indecomposable summons are O minus 1 in these guys. Which is, you know, it's basically about knowing what the projective modules over this algebra are. And there are some, you know, easy to well-known isomorphisms of projective modules that I'm sneaking in here. So what I was going to say, where these ones came from is actually, there's sort of a nice picture behind it. No, you'll notice there are never two consecutive 2s. Oh, whoops, I read the wrong thing there. So where these always come from is I can take a box with these contents and draw a line dividing it going from the top left corner to the bottom right. And then next to one of the red 2s, I read up from this corner this way, and for the other red 2, I read from this corner this way. So for example, this guy corresponds to cutting off one of the 2s. This guy corresponds to cutting off the other 2. This guy corresponds to doing it this way. So this is just employing some well-known, again, kind of like redundancies between projectives in the KLR algebra. All right, so how do we check something like this? So, like I said, I think it's better to do these ones with transition functions. So if I look at elements of the second wedge power of C4, these give me divisors on T star the Grassmannian. And actually, usually the ones you'll want to choose are the extremal vectors. So in this case, it would be the wedge powers of 2 basis elements. So if I take the wedge power of 2 basis elements, that cuts out an affine space in the Grassmannian. And the Grassmannian is glued together from those different affine spaces. So if I take the complement of this divisor, so I take proj and I invert that element of the second wedge power, I get an affine space, and the bundle is trivial on it. So I can pick trivializations on the 2 open sets and then look at the transition function between them. And because I know it's a vector bundle, I only need to check it's right on an open subset whose codimension is greater than 2. So it's enough to take 2 patches and find the transition function between them. And well, you just calculate. You can kind of have a better guess of what's going to happen by this thing I said about it being GL4 equivariant. So Bezrekhovnikov assures us that actually it will be GL4 equivariant, and that kind of reduces the possibilities quite a bit. All right, and this is just to give you a little bit of a feel for what's going on. So this is one of the ones that's I have to admit, I've forgotten. I think it's more that like you can construct, you know it's the same as the tilting generator that's constructed using the universal enveloping algebra. So it's kind of automatically equivariant based on that. Right, basically you can construct it in characteristic P by doing this stuff with the universal enveloping algebra. And so it's GL4 equivariant in characteristic P, and so actually the lift up to characteristic 0 must be equivariant as well. And I'm never using that in the proof, but it sort of helps me sort of think, okay, well this isn't going to be completely crazy. It's got to be something associated to a representation of that group. So for example here, right, I can write down an explicit diagram that gives me a map of O of -1 into this guy. And then the quotient is supposed to be O of 1. So I need to find a copy of the second wedge power in the sections of the quotient, and that's given by these diagrams.
Did you see the particular like complex guys over the O1 from the diagrams?
Oh, what the extension is? Well, I mean, I think it's better to think about the transition functions. It's sort of a little harder to draw a picture of the transition functions, so I sort of like this a little better. But, so for example, this is a different one. So what we're drawing here, so this is, I take x1 wedge x3 and I invert that. And this is, I take x2 wedge x4 and I invert that. And these, I get a rank 2 trivial bundle. And these are generators of the rank 2 trivial bundle on one patch. These are generators of the rank 2 trivial bundle on the other patch. And then you look at what algebraic relations they satisfy. And in this case, this is the one that gives me the tautological bundle. So I go back, I look up some Klucker coordinates, and I say, aha, this is the transition function for the tautological bundle between these two coordinate systems. All right. Thanks. I mean, I think we covered them during the talk.
So I have a question, a short one. Any hope how to generalize to T-star hierarchy and finding what's the, I mean, the goal is to make your abstract theorem more concrete.
Yeah.
Names for those two guys.
Yeah, it's an interesting question. I honestly don't know. So in general, the kind of underlying combinatorics is to have a like NK, KN rectangle. So this is sort of, this is a nice way of thinking about this quiver gauge theory. So I put the contents of these guys in the boxes. So this is, if I start counting down from here and over from here, it's the row plus the column, -1. And if you look at the number of boxes with a given content, it exactly tells you the dimension vector, with these corners telling you where to put the red strands. And so, I mean, I would hope that in general, there's some kind of combinatorics of what happens when you take a path across here and, think about this. Well, that will give you an idempotent. Oh, sorry, I did this the wrong way. Sorry, I'd done it the other way before. The path should go this way. It gives you an idempotent where what you do is, oh no, shit. No, I had it the right way before, I'm sorry. I do the path here. So I have two red strands that correspond to these corners. Right, so I have a red strand, let me call this M1, this is M2. I have a red strand with label M2. And then, so in the KLR algebra, if you look at what happens when I try to push a strand to the left, like what relation would stop it from doing that? Well, there has to either be a red strand with the same label to the left of it, or a black strand with an adjacent label. If I don't have one of those, I can just push that guy further left. So this M2 has to have something which has the same label here. That's the only thing that could be stuck on it. And then what could get stuck on this guy? It's exactly the guys with adjacent labels. M2 minus 1, M2 plus 1. And so one does the strands, sort of filling out the rest of the tableau up to this green line, and then on the other guy, you come from the other direction. Now there's an M1 stuck on this guy. There's going to be M1 minus 1, M1 plus 1 stuck on this guy, etc. And one would hope that there's sort of some nice answer based on what's the shape of this tableau for what coherent sheaf do I get here. But I mean, it also might just be kind of chaos, right? There's sort of no guarantee that you get a nice answer.
Do you know if any of this will connect to this low-set stuff on the...
I'm sorry, excuse me. I mean, you can get the Procesi bundle via a version of this story, though using something I hid from you, which is, you know, there's some choice of the mass parameter behind this. And if you have a cyclic quiver, then there's an extra mass parameter that comes from sort of the cycle. And you need to turn that mass parameter on as well. And that makes your relations more complicated. And so the Procesi bundle comes from this construction when you turn on that mass parameter, but only a little bit.
But he has also like an inductive construction of them, for like if you're doing build KC2 and you want to go to build K plus 1, he basically showed that we take the Nakajima correspondence between those two guys. It'll take the K Procesi bundle into the K plus version.
Yeah, I don't know. It might well be that there's some story there about, you know, pulling out strands, that's realizing a special case of, but I don't know.
More of a philosophical question, but yeah, so in these situations where the algebra functionality Coulomb branch does not have indeterminate resolution, you still write down these scalar algebras. Do you know that they're finite global dimension?
No, they wouldn't be. They would not. I certainly wouldn't expect them to be.
There's a phenomenon like, you know, like I talked in the compact case, like moduli spaces of sheets, like the resurface or something, there are lots of examples of these hyperpalars that don't emit, there are singular hyperpalars that don't emit like resolutions, but then people can still generate sometimes categories that behave like the right categories with proper variety that you could argue is this sort of, there is no commutative resolution, but there's still a non-commutative resolution. I was wondering if this...
Yeah, I don't think that's going to happen. I think like it's one of these things where, right, just as like you can resolve exactly as much as you can deform, sort of a similar kind of story.
Well, I think you know this. I guess the truth is about that, because you will let it be true. The scalar inductive algebra is this, is this thing that comes from the Coulomb branch construction.
So the thing I think you might be asserting, which I don't claim to have proven, but which I kind of suspect is true, is that if you sort of do a generic, BFN partial resolution, then the guy I told you will be a tilting generator on that. I hope that's true, but I can't prove it if it's not smooth. which would tell you it's sort of exactly as bad as that sort of generic BFN resolution is. Yeah. So I don't claim to have proved that, but I feel like it's probably true. So I mean, you know, somehow like morally, the way I would think about this is, you know, you have this sort of space of parameters where kind of along one axis you're deforming the actual underlying complex structure, and along another one you're kind of going into some non-commutative resolution. Maybe a good way to say this is,
I'm not following. So there are no complex structure that can turn on, right? While preserving the two grade, so crucial to the story. So these guys are rich. I mean, there's no complex structure information left.
yeah. Right, maybe a better way to think about this is, so, you know, if I want to do a resolution, I can think of this as like choosing the Kähler parameter, right? Looking at like H2 R of some resolution, right? And somehow you should think about these non-commutative guys as like thinking of this H2R as sitting in H2C and being on some like unit circle in the C version, right? And if you want to interpret it really literally, you can think about, I have the complex plane and I have the unit circle in the complex plane, and the literal positions of the red strands on the circle are some like complex rotation of the choice of Kähler parameter. Where choosing the Kähler parameter would mean choosing red dots here and saying, oh, actually, if I complexify, I'm not choosing just dots here, I'm choosing, like, I'm telling you what their radii are, but they could be anywhere in the circle. And this non-commutative guy somehow corresponds to them sitting on the unit circle. And this relates to this like picture of kind of thinking about derived equivalences as being like monodromy in the quantum differential equation, where you have, you know, different resolutions that correspond to these guys being far apart, and somehow you get derived equivalences between them by bouncing onto the unit circle and then having them pass each other.
I think once you are in this T structure that corresponds to the tilting bundle, then you can turn on Kähler module and make your space perfectly smooth without actually messing up the fact that this guy is a tilting generator.
Mm-hmm.
That's obvious in the A side. If you go the other way, you want to turn off the B field and just have real Kähler moduli, then things become very, very complicated, right? And you have to you'll get some non-trivial derived equivalence. But once you're at this point where all your points are on the circle, when you just have the B field, this guy is your tilting generator, then you can turn on Kähler moduli at will. This is somehow the magic of it, right? Yeah. You'll be able to resolve it in any chamber, and this guy will still be tilting.
You will have non-commutative resolutions.
Yeah, exactly. So you can, this guy will exist on a smooth space too, and still makes sense on both sides.
But I mean, somehow.
The mirror symmetry picture makes it very clear, like exactly at which point in the modular space you are at, and what are you allowed to do without going out of the chamber with this guy is your tilting generator.
Right, but I think, you know, Daniel was asking about, like, if you choose generic real mass parameter, what if that's not smooth, but somehow you can get it non-commutatively smooth? And I think the answer is you should be kind of equally smooth at all generic choices of parameter.
Even in non-generic ones, as long as you don't choose the B field, you can do anything you want with Kähler moduli, and everything is totally fine. It's just that if you want to turn on the B field so that you understand, I mean, usually, right, if you just think of your geometry, you don't have any B field at all, right? Then you're in this kind of real line situation where then you have a very non-trivial derived equivalence that takes you from there to this exotic T structure to the other side.
Right, but
the exotic T structure, you can turn on Kähler moduli.
I don't understand exactly how what you're saying is related to the question. The question is the following. The question is, suppose you
Right, imagine you took like a non-minuscule highest weight.